So in this clip, we're going to take the custom coordinates that we worked out in the last clip and put them to use to solve this integral right here. So if you were to be given such a thing, you might say, okay, how am I going to integrate this? It's got this god-awful exponent, x plus y over x minus y. And you need to figure out how to sort that out. Well, the idea is that if you were to put u equal to x plus y, and then v equal to x minus y, then this would become something much simpler. Namely, you'd have an integrand of e to the u over v, and it's not super pretty, but it's actually pretty easy to integrate. So that's the idea that we're going to be working with. Okay, and then this is going to be integrated over this region right here. So now we have the question of trying to figure out what would be the parametrization domain for this region. In other words, what patch of the UV plane gets mapped onto this region by these coordinates. Okay, so let's see. So what we can do is we can look at how the transformation goes. I mean, one thing is you can try and say, hey, how did something get here? The other thing is you can look at the inverse transformation and say, what does it look like under the inverse transformation? So we're going to take our u equals x plus y, v equals x minus y, and then solve for x and y. So for instance, if you just add these equations together, you get u plus v equals 2x, and the y's cancel. And then you've already figured out that x equals u plus v over 2. And by a similar calculation, you get that y is u minus v over 2. And these are the coordinates that we worked out previously, right? So we can use this to find the parametrization domain. So this is our way of looking backwards. Okay, so let's see. So, the other thing, and I should have mentioned this before, is that if we take these as our coordinates, then take a look at what does it look like if you have like u equals 1 or v equals 1, like the coordinate curves for these particular coordinates. So x plus y equals 1, well, that looks like a diagonal line like this. X plus y equals 0, x plus y equals minus 1. And then v equals 1, that looks like this line here, v equals 0, v equals minus 1, etc. So we have these diagonal lines as our coordinate grid. And since our region has these diagonal lines that go in correspondence with that, that's kind of a good thing. That's telling us that this is going between v equals something and v equals something else. So that'll make it nice to set up our parametrization domain. Okay, so what is the parametrization domain? Well, I'm going to mess around with this little figure that I drew, so I'm just going to copy it here. Okay, so let's look first at the green part over here. This is where x is equal to 0, and we've got y between minus 2 and minus 1. So that means that on our output here, we've got, or our parametrization domain, I'm just going to call it parametrization domain so I don't have to mess with which direction the transform is going. Okay, so let's see. This is x equals 0. So let's see. So then if I write down what the maps are there, that means I've got u is equal to x plus y, but x is 0, and v is equal to x minus y, which is just minus y because x is equal to 0. And so that's telling me that u is equal to minus v. So that's a diagonal line going this way in the uv plane. And we're going from y equals minus 2 to minus 1. So that means that v is going to be going from 1 to 2. Okay, so it's this one. All right. And then let's see what we've got going on for over here on the other side. So this is where y is equal to 0, and we've got x going between 1 and 2. So let's see. So if y is equal to 0, then u is just going to be equal to x, and v is just going to be equal to x. By the way, these equations, I'm just pulling everything from this, what we had back in the very beginning, which was that our u was equal to x plus y, v is equal to x minus y. That's so I'm just getting these equations from doing y equals 0, because that's what the purple line represents, yeah? And so that's going to be this one right here. Okay, so let's see. So now let's keep doing the same whole thing, but now we'll do the other parts. So this one right here on the top, this is where x minus y is equal to 1. So that's v equals 1. And we're going from this diagonal line right here to this one right here. So this is x plus y equals 1. That's not even visible, is it? Here, let me switch to a darker green. And this is x plus y equals minus 1. So I've got, and so x plus y, that's u. So we're going from u equals minus 1 to 1, and we're at v equals 1. Okay. And so that's cruising along at height 1 there. And then for the last side, well, it's already a dead giveaway that it's going to be this one right here. But just to see that everything's legit, this is where we have x minus y equals 2. So that's v equals 2. And then we're going from this to this. And so the top, so the one bounding up here, that's where x plus y equals 2. And the one down here, this is the line x plus y equals minus 2. So we're going from u equals minus 2 to u equals positive 2. So there's minus 2 to positive 2. And we're doing it at height 2. So that's exactly the figure that we've got. Okay, so now we have our region. And we say, okay, so this is going to be our parameter domain D. And this will be an elementary region if we do the du integration first. Right, we'll be going from green to purple, and we'll pick up those slices between orange and red. So I can go ahead now and set up my integral. So let's see, so we go from v equals 1 to v equals 2. And then we go from the lower boundary, u equals minus v, up to the upper boundary, u equals v. Right, this is coming from stuff that we already found right here. And then we've got e to the u over v. And then we've got our Jacobian. So that's going to be 1/2 dv du. Oh, sorry. du dv. And then I can just go ahead and integrate this sucker. And it's at this point, it's boring mechanical stuff that you know how to do well. So we integrate that guy and we get v e to the u over v. From u equals minus v to u equals positive v dv. And so that's 1/2 integral 1 to 2. Evaluating that guy, we get, well, the v comes on for the ride, and then we get e to the, and they cancel and give us 1. On the other end, they cancel and give us -1 dv. And that ends up giving us 3/4 e minus 1 over e. And we are done. Except wait, there's more. So what we found from our transform here, this is the parameterization that we're using, and we computed the Jacobian for this guy and found that it was equal to -1/2. What if we were to look at the reverse transform? So suppose we were going in the opposite direction. Now we've already worked out what the formula is for going in the opposite direction. So here's our inverse, the inverse transformation, and so let's see. So the Jacobian for this one is going to be du v over dxy, and that will be, let's see, so ux uy vx vy, and taking those derivatives. So here, let me just grab the transformation again. There's the transformation. So taking the partials of those guys, I get 1 and 1 and 1 and -1. And so then that gives me -1, and then I subtract a +1, and I end up with -2. And so the moral of the story here is that if I look at the Jacobian of the inverse transform, it's equal to the inverse of the Jacobian of R.